Hi guys, this is Mr. Ward. We're getting started on our last unit before the end of the first semester, Unit 8, called Linear Programming. It's actually a branch of math that you will study, one of the few that was created within the last 100 years. It was developed by a gentleman in Europe during World War II. It's all about maximization and minimization. How can you maximize profit? What a production quota would be. How you could minimize cost. It uses a lot of graph theory with inequalities and shaded regions, so we're reviewing that. And we'll also review how to find solutions, because those are going to be corners or vertices that we will use. All right, let's get started. We'll just review from Algebra 1 and 2 how to solve systems. We did these a little bit ago. We're going to do it three ways. We're going to do substitution, we're going to do elimination, and we're going to support it graphically. So substitution means I'm going to take the first equation, I'm going to solve it for x. Move that y over, x equals y minus 5. In the other equation, wherever I see an x, right at the beginning, oops, sorry, that's a 4. Wherever I see an x, which is right at the beginning, I'm going to replace with y minus 5. Now I have a single equation, which is in one variable. Combine like terms, 3y minus 5 equals 4, 3y equals 9, y equals 3. I'm not done, I got to then plug in for x. X equals 3 minus 5, x equals negative 2. So the solution is negative 2 comma 3. That's substitution. Elimination, if you remember, is eliminating. You get a variable to drop out. I'm going to take the top equation and multiply it by negative 1. Negative x plus y equals 5. X plus 2y equals 4. X's that get eliminated drop out. Again, 3y equals 9, y equals 3. And I plug it back in and still get that negative 2 comma 3. Now, graph theory, the third way, you've got to get them both y ready. Y equals. The first equation will be y equals x plus 5. Take as many liberties as you want, just make sure you do it right. Second equation, subtract the x, divide by 2, y equals negative a half x plus 2. How do I graph? Y equals x plus 5, y-intercept, 1, 2, 3, 4, 5, slope over 1 up 1. I'm going to use my line tool here, which I can. We have over 1 up 1, so it would be like that. And I'll extend it a little bit more. I know my answer is going to be in the second quadrant, so therefore I'm more than far enough. How do you graph the line y equals negative a half x plus 2? Intercept is at 2. Slope is down 1 over 2, down 1 over 2, down 1 over 2. Up 1, back 2. There's my line right there. And they're going to intersect at this point. What is that point? Negative 2, comma 3. Solved algebraically, supported graphically. All right, let's solve this system of equations graphically, but we're going to graph differently. We're going to graph using what's called the x-intercept, y-intercept method. What does that mean? We're going to take the first equation, 2x plus y equals 10. To find the x-intercept, where it crosses the x-axis, that means y equals 0. So I'm going to plug a 0 in for y, leaving me with 2x plus 10. 2x equals 10. Therefore, x equals 5. What did I find? Where this blue line would cross the x-axis. The other one, 2x plus y equals 10, replace x with 0. I get 0 plus y equals 10. Y equals 10. There's my x-intercept, y-intercept. So if I was going to graph this line, I'll call this the blue one. We'd have an x-intercept of 5, 0, 1, 2, 3, 4, 5. We'd have a y-intercept of 10, 1, 2, 3, 4, 5, 6, 7, 9, 10. And make a line go through there. Make it blue, match. Right there. Let's do the second one in red. little quicker this time. X-intercept. 2x equals 10, x equals 5. Pardon me. 2x equals 16. Sorry about that. I was looking at the wrong equation. X equals 8. 4y equals 16. Y equals 4. A y-intercept of 4. 1, 2, 3, 4. X-intercept of 8. 6, 7, 8. We connect those with a red line. So, not only that, we could then solve the system. Where do they intersect? They intersect at this point right here. What is that point? The solution would be 4, 2. I could verify that algebraically using substitution or elimination. I just solved it graphically. So again, a little graph theory, a little basic algebra. Now let's move on. We're going to review graphing linear inequalities. And how do I graph that? Notice it's not y equals 3x minus 2. It's y is greater than 3x minus 2. Well, let's start with the simple one. The y-intercept is negative 2. The slope is up 3 over 1, up 3 over 1, down 3, back 1. And now, the new thing is, what does greater than mean? Well, it's a solid line or a dotted line. Dotted line means not equal. Solid lines means equal. So in this case, it's a dotted line, and it's greater than, so I'm going to shade up. So let's graph this line. It's going to be a dotted line. This dotted red line here. And that means the line itself is not included in the solution region. So which half are we going to graph? Up. If that was a tree and it would fall down, which in this case would be right. So up would be the opposite, so somewhere over here. Every point in this red shaded region would be a solution. I'm going to pick one. Negative 2, 1. Does that work in the inequality? Let's see. 1 is greater than 3 times negative 2 minus 2. 1 is greater than negative 8. It sure is. And I could just as easily pick a point that is not going to work, plug it in, show that it doesn't work. All right, let's do this one in blue. Let's use our new x-intercept, y-intercept method. So I'm going to label this as the x-intercept. 2x equals 12, x equals 6. Y-intercept, 3y equals 12, so y equals 4. I'm going to count by 2 since my numbers are small. Mark up here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What are my intercepts? X is 6, y is 4. X is 6, y is 4. Let's go back up. It is a solid line because it's less than or equal to. And we're going to shade down. So when I connect these two points, solid line shaded down, and I'm going to do something that we're going to do a lot of because, again, this is all about applications, maximizing and minimizing things, and you rarely have things like negative products. So we're often going to be in the first quadrant. And what first quadrant inequalities are going to mean is, first quad, sorry, spelled it wrong. First quadrant. So, there we go. First quadrant. Sorry, I wasted a little bit of time here. X is greater than 0, y is greater than 0. That would put us in the first quadrant. All right. What would these corners be then? They would be 0, 0, 6, 0, and 0. Let's review real quick the inequalities, and then we'll do one with a little more to it. If you're going to graph, get into standard form, slope-intercept, or this new x-intercept, y-intercept method in the first quadrant. Remember, if you're going to get y ready and you end up multiplying or dividing by a negative, you got to flip the inequality. Greater than becomes less than and vice versa. Interpret the inequality line, whether it's solid or dotted, and which way you're going to shade up or shade down. The vertices of the region, the corners, we're going to use either graph theory to find those intersections, or we're going to solve them algebraically. All right, one that's got a few pieces on it right here. Sorry about that, I had a little typo. The second one is greater than or equal to. So let's do the first one. X is greater than 0. I'm going to do that in green. X is greater than 0 is just the x-axis. I'm sorry, is the y-axis, my bad, because it's x-intercept, or x is greater than 0. And it's going to be a dotted line. And we're going to shade greater than. Well, this is the only one where you can do that whole idea of which way the tree falls. So I'm going to just say that way, greater than. All right, the next one I'm going to do is actually the third one. I'm going to do this in red. Y is less than x. Again, it's going to be dotted. And y is less than or equal to x is right through 45 degrees. It's going to look just like that. And I'm going to shade down. You know what? I'm going to change that. I'm going to change this one as well. I'm going to make this y is greater than x. So that means I'm going to shade up. Just so I have a nice, better feasibility region. You can see in a minute. Okay. So if I'm up from the red and I am right from the green, I'm in the top left quadrant. Now let's do the third one. I'll do this in blue. 3x plus y is greater than or equal to 12. X-intercept. 3x equals 12. X equals 4. Y-intercept. Y equals 12. So if I count over 4, 1, 2, 3, 4. Up 12. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. I connect those two blue dots. It's going to be a solid line. And it says greater than, so I'm going to shade up. So I'm going to put a little arrow like this. And where my shaded region would be is this region right here. That's called an unbounded region. Sometimes we have those. Sometimes we don't. We have bounded regions. Unbounded simply means it keeps going on forever. The only vertices I would see in this problem is this corner right here and this corner right here. So graph that green one, graph the blue one, graph the red one, that's solution region. And if you picked any point, let's pick a point nice and in the middle here. Let's go. 4, 8. 4, 8 should work in all three inequalities. Is 4 greater than 0? Yes, it is. 4 times 3 is 12 plus 8 is 20. Is 20 greater than 12? Yes, it is. And is 8 greater than 4? Yes, it is. If you weren't in that shaded region, then that would mean you'd fail at least one of the inequalities. All right, guys, very good. That's day one, introducing, again, inequalities as well as solving systems of equations. Great work, and we'll start on day two with some linear programming next.